So without further ado, let's go to step 1. We want to derive the second order equation. So what you're going to find here is that there are 2 techniques for solving these circuits. Okay? So there are 2 techniques for deriving this equation. And you're going to see that one technique is known as the direct method, and the other one is known as the matrix method. Okay, so one of the things that I want you to, matrix/operator method. Because you do convert it into an operator. When you convert it into an operator, it turns out that you make it into an algebraic equation in the end. This method, I will introduce it for a little bit. I don't want you to use that method. There are certain circuits that when you get into the direct method, that if you use with the direct method, you will go around in circles forever. It's like an infinite loop. You just keep going around and around and around. The matrix or operator method, we'll get to it right away. And I kid you not, this is far superior. This is almost like a Laplace transform. It's not a Laplace transform, but very close to it. And so what we're going to do here is that, so the overall view, the overall viewpoint is that we use KCL and KVL to generate 2 first-order equations. That's what we do. When we do this, we then substitute. I see that I've left an R out of here. Then we substitute. Then we substitute one equation into another to generate a second order equation. And you're going to see that there's this very unique process that we're going to go through here. So we'll use KCL to do what? Relate IC and IL. Then we're going to use KVL to generate VC and VL. And we're going to relate those 2 quantities. And when we do that, we typically solve for one variable in one set of equations and plug it into the other. And then it turns out that we get a second order equation from that. So the overall viewpoint looks something like this, where in the end, what we're going to get here is that we're going to get a second order equation that looks like this. And since our force term here is always going to be a constant, you're going to see that it's going to be exactly like this shape right here. So my experience here is that one of the things that you want to pay attention to here is note that capacitors and inductors are what? They're passive elements. I've been saying this since almost day one. And if you don't treat them as passive, you will not write down the correct equation. And I know that's slippery business sometimes. But you got to remember, capacitors and inductors are passive elements. They have no EMF to bring their charge back up to a higher potential. So, that's it. So, let's go write it down now. Here's problems. So, let's write down. So, here we go. So, this is method 1 now. So the only reason why I'm using direct substitution is to sort of like have you sort of like follow me where I'm going. But in the end, I'm going to rely only on this second method, this operator matrix method. That is by far my favorite. It's by far the favorite of the students of the past because it's harder to make errors. So what you're going to have to do here is that you're going to have to trust my notation for a little bit. And then we want to drop all of this notation. All of it. So the first thing that I want to do here is that I want to define variables x1, x2. This appears to be like a silly thing. It's not a silly thing. It's you'll see that it sets up so that how do we look at their equations, and furthermore, it sets it up for helping us with the initial conditions later on in the problem solving. So what we do here is that we define variables so that we do this. So if I set the variable x1 equal to IL, and I set the variable x2 equal to VC, you could see then that what I'm seeing here is that I set x2 for the variable we are solving for. So if I want to solve for variable, the voltage of the capacitor, I set x2 as that. So therefore, the only other variable, IL, has to be x1. Or I could reverse it. If I want to solve for the current of the inductor, then I set x1 equal to VC and x2 equal to IL. So in this case, we're solving for IL. And then I go to the next step. Step 1.2. So then what we're going to do here is that we want to derive two first-order equations using Kirchhoff's laws. So there's 3 steps here. Okay? The first step here is that you want to apply KCL to relate IC and IL. We want to apply KVL to relate VC and VL, just like we've talked about in the past. And then there's the resistor term. And this becomes an important piece. You want to rewrite all resistor variables in terms of VC, IL, IC VL in terms of those four variables. Okay, this is step 1.3. And then here what we want to do is that we want to rewrite IC and VL using IC equal to C dV dt and VL equals to L d IL dt. And identify equations 1 and 2. Now it turns out that equation 2 is the term that has the derivative of the second term right here. Step 1.4. You then want to derive the second order equation by direct substitution. So now you want to derive the second order equation using direct substitution. That means that you want to sub equation, let me make sure, you sub equation 2 into equation 1. And finally, the last step here is that you want to check your equation and determine the force response. Check that out. That's step 1. Right, step 1 has 5 pieces to it. And what's important here is, remember what I said here. I don't want you to memorize this process. You'll see that when we start practicing it, when you get better at KCL and KVL, it's a very natural process. And my experience over the years is that people rarely miss deriving the second order equation. That doesn't mean that you're going to derive it correctly, but in general, it means that the majority of the people get it. So let's go do this. So what I'd like to do here is that I'd like to first go through those steps first through a circuit that you don't have the example to, and then we'll do the example that's in your example packet for chapter 9. Okay? So here's an example that we want to go through. So what I have here is that I have a circuit that looks like this. And there's going to be some circuits where I will have to give you the polarity, that you would not know what the polarity of the voltage across the capacitor, the current of the inductor, or some resistors. I will have to give it to you. But in this case, I think it's pretty obvious that this circuit immediately tells you that it has to have what? That polarity, it has to have this current, this direction, and it has to have that voltage like that. So what I'll do here is that I'll write, and I would say, derive this equation. Okay? So if I go to derive this equation, what I want to do here is that, let's say that I'm asking to do what? I want you to derive the inductor's second order equation. Okay, so this is what we really want to solve for, that equation across that guy. So that immediately says what? I'm going to define my variables, x1 and x2. Since I am solving for the inductor current, I'm going to write x2 as IL. So therefore, I have no choice but to call this PC. So I just did step one. Right? That seems a little bit silly that we're doing that, but it really makes a difference as we go through later steps. So there's step one right there. So now if I go to step two, what do I got to do? I gotta derive the first order equation. Okay? I'm going to derive two first order equations. So now if I look at this, I'm going to do what? So I got to relate the two currents together using KCL. So here we go. So I'm going to do KCL. So when I look at KCL, well, these two are in series. So I immediately say what? I got to write IL equal to IC. They're in series. And then I got to apply KVL, and I got to relate these two voltages together. Now note, these two are in parallel, so it doesn't make sense to talk about the voltage here, because this is how we're going to solve for the voltage here. So the voltage across the one must be the sum of these two voltages. So then I'm going to write that VL plus VC equals the voltage across the 1 ohm resistor. Okay? Now, what you now go do here is it says what? Rewrite all the resistor variables in terms of these things here. Well, when I look at this guy right here, I need to rewrite this guy in terms of either IL, VC, VL, or IC here. And when I look at this thing here, I'm looking at this node right here. You can see that I have what? I source coming in, IL going out. So therefore the current through the 1 ohm resistor must be I source minus IL. So now if I come in here, what I'm going to do now is that I'm going to rewrite using KCL. And when you see that, you can see that I source minus IL has to be the current across the 1 ohm resistor. So if I look at that, since V and I for a 1 ohm resistor is the same, I'm then going to replace this with IS minus IL. And that's the end of step 2. So remember, you got to replace the resistor values using these quantities. So now, what I'm going to do here is that I'm going to come in and I'm going to rewrite everything, all of the ICs, all of the VLs in terms of these two, and then I'm going to identify the equation 2 here. So then I'm going to come over here and I'm going to do step 1, 3, and I'm going to rewrite IC and VL as follows, and identify equation 1 and 2. So then if I look at the first equation here, you can see that I have to rewrite IC. So I'm going to see that I'm going to get IL equals C dV dt. But what is C? C is 1/2. So I'm going to write this as 1/2 dV dt equals IL. There's my first equation. And you can see that this does not have the derivative of IL. So therefore, this is equation 1. If I look at the second equation now, see this IL term? I'm going to bring it to the other side. So if I look at this, I'm going to have IS is going to be IL. Then I have two terms, VL plus VC. And so now I'm going to replace VL with this term, L di dt, which will be IL plus L di dt plus VC. But IL, or L, is 2. So then I'm going to write the equation IL VC plus 2 dt IS, and here's my second equation, and you can see that this is really the term we're looking for. This term right here. That's the term that we're looking for, and so this is now equation 2. So then following this process here, to derive the second order equation, we're just going to substitute equation 2 into equation 1. So ultimately, what this is really for is that, so we want to derive second order equation. So what we'll do here is that, so we're going to sub 2 into 1. But you got to be careful here, because what we're really doing here is that we want to get rid of VC in this equation. So we solve for VC, and then we plug it into here, so that we eliminate VC from the equations here. So what we do here, so what this means here, is that we solve for VC and sub into 1. So starting with equation 2 here, now if I solve for VC, you can see that I got to take this term over here, that term over here. So then I'm going to get VC is going to be IS, IL minus 2 di dt. Okay? There's equation 2. And then I plug this guy directly into 1 for VC here. And sub into 1 again. So then if I look at this guy, I'm now going to write what? 1/2 d dt. So then I'm going to write d dt. And then I'm going to plug this guy in. IS, IL, 2 di dt. And then this guy has to equal IL. So you can see that by doing this process, I remove VC from the equation. So now what am I going to do? I'm just going to take the derivative of all of the terms. So probably the first thing that I'm going to do is I'm going to take that 1/2 factor and I'm going to multiply everything by 2. So I don't have to carry the 2 with me. So then my first term then becomes dis dt minus di dt minus 2 di dt squared equals the 2 IL. And because these two terms have a minus sign, I'm going to take them to the other side. So then if I rewrite this guy here, this will then look like this. It's going to be 2 di dt plus dl di plus 2il equals to dis dt. And that's my second order equation right there. Now, what I would do now is that I would check this equation. So we want to find out whether this equation is reasonably good. So for all intents and purposes here, let's say that this term is a constant. If this is a constant, what is the inductor current going to go to at steady state?
0.
Should go to 0 because the capacitor opens up and all of the current through the inductor goes to 0. So what we could say this here is that if Is is equal to a constant, we just showed here that the inductor current at t equal to infinity would go to 0. Does that, physical looking at the circuit agree with that equation? Well, at t equal to infinity, IL will go to a constant. So I'm now going to take this B term and I'm going to substitute it into my equation. And you can see that this will be what? And then derivative of a constant is 0, and you can see that this guy goes to 0, this guy goes to 0, and so the only way this could be true is if phi is equal to 0, which is exactly what we expected. Now if we had a a time-dependent source, then we would have to look at how the derivative of this guy relates to that guy right there. And it would be the exact same way. So, why am I so interested in deriving these equations 1 and 2? When we go to solve for the initial conditions, note that this equation is the derivative of the inductor. When we have to solve for the initial conditions for a second order circuit, we need not only IL, but we need the derivative of IL. That's where we're going to get that term right there. So when we need to go look for the initial conditions, we need this equation. That's why it's worth going through this and identifying what is equation 2. Because then we could just come in and just kind of pluck it